right. Hello, everybody. Welcome back. I hope you're having a wonderful day so far. My name is Michael. I am back here streaming like usual. Here a little bit earlier today than normal. It's Friday, so I can stream a little bit earlier, but I am going to be cutting it a little bit shorter today. I'm going to a concert later this evening. So today won't be as long, but I wanted to come in and get some studying in nonetheless and get some work done. So let's get right on into this. How about? I am going to be. All right, let's go here. Pop this guy out. Copy that. All right. Nice. Got that all situated, and let's go ahead and get into this. So we'll warm up with just a little bit of reading in DSA. We're almost done with the chapter here. Okay. Yeah, we're here. 10.4.2. Hello, Mahan. Welcome in. All right. 10.4.2 of DSA in Python. We are back in data structures and algorithms in Python. We are on page 443, 444. We're about to finish this chapter, so we'll probably finish here at this stream. And then we'll get moving on here to the next one. Thank goodness. I've been done with hash maps, tables, and skip lists for a while. I'm done with this chapter. All right, let's get on to it. As we have shown above, skip lists provide a simple implementation of a sorted map. In terms of worst-case performance, however, skip lists are not a superior data structure. In fact, if we do not officially prevent an insertion from continuing significantly past the current highest level, then an insertion algorithm can go into what is almost an infinite loop. It is not actually an infinite loop, however, since the probability of having a fair coin repeatedly come up heads forever is 0. Moreover, we cannot infinitely add positions. We cannot infinitely add positions to a list without eventually running out of memory. In any case, if we terminate position insertion at the highest level h, then the worst case running time for the algorithm performing the get item, set item, and delete item map operations in the skip list with n entries and height h is O of n plus h, where the worst case performance occurs when the tower of every entry reaches the level of h minus 1, where height of h is the height of this sequence. However, this event has very low probability. Judging from this worst case, we might conclude that the skip list structure is strictly inferior to the other map implementations discussed earlier in this chapter. But this would not be a fair analysis, for the worst case behavior is a gross overestimate. Okay, so this is saying, right, in skip lists, you do have some probabilities, however small, that you might fill up this entire, subsequence mapping here of the skip list if you hit heads on every single, value up to some height of h. Or in a case where you hit heads infinitely or indefinitely, right, on some value over and over and over again to exceed, infinitely upwards. Now, the probability of likely that happening is 0, as you will hit head tails some other time, but it still is a possibility in some cases. So it's interesting to think about. Bounding the height of a skip list. Because the insertion step involves randomization, a more accurate analysis of skip lists involves a bit of probability. At first glance, this might seem like a major undertaking, for a complete and thorough probabilistic analysis could require deep mathematics, and indeed, there are several such deep analyses that have appeared in data structures research literature. Fortunately, such an analysis is not necessary to understand the expected asymptotic behavior of skip list. The informal and intuitive probabilistic analysis we give below uses only basic concepts of probability theory. Let us begin by determining the expected value of the height h of a skip list S, with n entries. Assuming that we do not terminate insertions early, the probability that a given entry with a tower of height I greater than height I greater than or equal to 1 is equal to the probability of getting I consecutive heads when flipping a coin. That is, the probability is 1/2 to the power of I, right? Hence, so if you were saying if you have some height of I in this case, if you were to get heads over and over again, it would have to hit 1/2 to the power of I, the power of its height, right? Just basic rules of probability. Hence, the probability or P sub I that the level of I has at least one position at most is this here. For the probability that any one of n different events occurs, at most the sum of the probabilities that each occurs. The probability that the height of the sequence is larger, or the skip list, than I is equal to the probability that the level I has at least one position. That is, it has no more than pi, which means that the height is larger than, say, 3 log n with a probability at most. So the probability 3 log n is... okay, this is getting complex here. For example, if n equals 1,000, the probability is a 1 in a million long shot. This probability is a 1 in a million long shot. More generally, given a constant of c greater than 1, h is larger than c log n, with probability at most 1 divided by n to the power of c minus 1. That is, the probability that h is smaller than c log n is at least this equation here. Thus, with high probability, the height h of a sequence is O log n. Yeah, I'm not really sure what happened there, but let's take this section here. Let's say, can you please break this down? Hey, Glime, how's it going? Welcome in, dude. Hey, Wing Hong, welcome back. Let's walk through this slowly and clearly. You're reading a probabilistic analysis of a height of a skip list, which can feel a little dense, but it's actually pretty approachable with some basic ideas. Here's a breakdown. The core idea: when you insert an element into a skip list, you flip a coin to decide how tall the tower of pointer levels should be. Each additional level, or height, is only added if the coin keeps landing on heads. So the chance of a tower reaching level I is the probability that height is greater than or equal to some level of I is equal to 1/2 to the power of I. Got you. Step-by-step breakdown. Probability a node reaches height I. Let's say you looking at a specific node. What's the probability it reaches level 1? Always 100%. Level 2 is a half. Level 3 is a fourth. Level 4 is an eighth, and so on. So the probability a node reaches the level of I is 1 over 2 to the power of I. Okay, got you. Analyzing search time in a skip list. Next, consider the running time of a search in a skip list, S, and recall that such search involves 2 nested while loops. The inner loops perform a scan forward on the level of S as long as the next key is no greater than the search key, and the outer loop drops down to the next level and repeats the scan forward iteration. Since the height of S, or the skip list, is O log n, with high probability, the number of drop-down steps is O log n, with a high probability. So we have yet to bound the number of scan forward steps to make Let n sub I be the number of keys examined while scanning forward at some level of I. Okay. Observe that after the key at the starting position, each additional key examined in a scan forward at level I cannot also belong to level I plus 1. Right, they're not found. If any of these keys were on the previous level, we would have encountered them in the previous scan forward step. Okay, got you. Thus, the probability that any key is counted in n sub I is a half. Therefore, the expected value of n sub I is exactly equal to the expected number of times we must flip a fair coin before it comes up on heads. This expected value is 2. Hence, the expected amount of time spent scanning forward at any level is O of 1, since S, or the skip list, has O log n levels with a high probability. A search in the skip list takes expected time O log n. By a similar analysis, we can show that the expected running time of an insertion or removal is O log n. Space usage in the skip list. Finally, let's turn to space requirements of a skip list S with n entries. As we observed above, the expected number of positions at level I is n divided by 2 to the power of I, which means that the expected total number of positions in S is, where we have the sum of, from the range of 0 all the way up to some height, n over 2 to the power of I, which becomes 1 over 2 to the power of I times n. We bring out n out front. So using prop 3.5 on geometric summations, we have this. So you take the half is equal to half h plus 1 minus 1 over half minus 1 equals to 2 times this equation, which is less than 2 for all h greater than 0. Hence, the expected space requirement of the skip list is O of n. Table 10.4 summarizes the performance of a sorted map realized by a skip list. Okay. All right, 10.5 here. That was dense. That section sucked. It's all right. We're just getting a good introduction and a good breakdown of these things, and we can always come back if we need to use any of these structures and really take a look at our notes and at the text, and we'll know exactly where to look. We conclude this chapter by examining several additional abstractions that are closely related to the map ADT and that can be implemented using data structures similar to those for a map. A set, okay, we know this. We know what a set is. So a set an unordered collection of elements without duplicates that typically supports efficient membership tests. In essence, elements of a set are like keys of a map without any auxiliary values. A multi-set, also known as a bag. Okay, so we'll say similar to a map without, similar to keys in a map without values. Okay, a multi-set, also known as a bag, is a set-like container that allows duplicates. A set-like container that allows duplicates. And a multi-map is similar to a traditional map, similar to a traditional map in that it associates values with keys, However, in a multi-map, the same key can be mapped to multiple values. Okay. Multiple values. But the same key can be mapped to multiple values. For example, the index of this book maps a given term to one or more locations at which the term occurs elsewhere in the book. The set ADT. Python provides support for representing the mathematical notation for a set through the built-in classes frozen set and set, as originally discussed in chapter 1, with frozen set being an immutable form. An immutable form of a set. Both of these classes are implemented using hash tables in Python. Python's collections module defines abstract base classes that essentially mirror these built-in classes. Although the choice of names is counterintuitive, the abstract base class collections.set matches the concrete frozen set class, while the abstract base class collections.mutable set is akin to the concrete set class. Okay, so set is frozen class, mutable set in the collections module. In our own discussion, we equate the set ADT with the behavior of the built-in set class, and thus the collections.mutable set base class. We begin by listing what we consider to be the 5 most fundamental behaviors of a set S. Okay, so behavior, five fundament behaviors of sets. Number 1, set.add element, right? We know that one. Add element E to the set, element E to the set. This has no effect if the set already contains E. Number 2, s.discard E. Remove element E from the set if present. This has no effect if the set does not contain E. Number 3, E in set, E in S, which returns true if the set contains element E. In Python, this is implemented with the special contains method. Number 4, right, length of the set. Return the number of elements in set S in Python. This is implemented with the special method under length. Type it fast today. Feeling good. And then iter S, generate an iteration of all elements of the set in Python. This is implemented with the special method dunder iter. Cool. In the next section, we will see about 5 methods. So we'll see that the above 5 methods suffice for deriving all other set behaviors. Those remaining behaviors can be naturally grouped as follows. We begin by describing the following additional operations for removing one or more elements from a set. So s.remove removes element from a set. If it does not, it contain it raises a key error. Set.pop remove and return arbitrary element from the set. If the set is empty, raise a key error. And set.clear remove all elements from the set. So then we'll say what between set.discard and set.remove. The difference between set.discard and set.remove in Python comes down to how they handle missing elements. Set.remove removes element X from the set and raises a key error if it's not in there. Discard removes element, does nothing. Remove gets mad, discard doesn't care. Okay. So we'll just say like this: fundamental behaviors of sets. Then we'll say here additional methods of sets. We'll do this here and go set dot remove element E, right? And this will remove element E from the set if the set does not contain E, raise a key error. Number 2, s.pop, right, will remove and return an arbitrary element from the set if the set is empty, raise key error. Okay. Number 3, and set.clear, remove all elements from the set. Okay. The next group of behaviors perform Boolean comparisons in between two sets. S equal is returns true, is not equal, right? Less than is if it's true if S is a subset of T. If it's less than, if it's a proper subset. If it's a superset, if it's a proper superset. Is disjoint returns true if S and T have no common elements. Okay, so I'm going to take this here, like that. Like so. Okay. We are almost done with the chapter. Uh, 10.5.2 Python's mutable set abstract base class. To aid in the creation of user-defined set classes, Python's collections module provides a mutable set abstract base class, just as it provides the mutable mapping abstract base class discussed in section 10.1.3. The mutable set base class provides concrete implementations for all methods described in section 10.5.1, except for 5 core behaviors: add, discard, contains, length, and iter. That must be implemented by a concrete subclass. This design is an example of what is known as a template method pattern, as the concrete methods of the mutable set class rely on the presumed abstract methods that will be subsequently provided by the subclass. For the purpose of illustration, we examine algorithms for implementing several of the derived methods of the mutable set base class. For example, to determine if one set is a proper subset of another, we must verify two conditions. A proper subset must have size strictly smaller than that of its superset, and each element of a subset must be contained in the superset. And in implementation of the corresponding dunder IT method, based on this logic, is given, or less than is given in code fragment 10.4. So it supports where this set is less than some other t. So it returns true if the set is a proper subset of the other. So if it is, it has to have a less elements, and all the elements have to have been in the superset. So if the length of the self is greater than or equal to the length of other, return false. It's not a subset. It's not less than. For every element in the self given, if the element is not in the other, we're going to return false, and then we'll return true if it's successful. A possible implementation of the immutable set with the dunder less than method, which tests if one set is proper subset of another. As another example, we consider the computation of the union of two sets. The set ADT includes two forms of computing a union. The syntax of S bar T should produce a new set that contains equal to the union existing sets S and T. This operation is implemented through the special dunder method of dunder or in Python. Another syntax as S bar equal to T will use to update the existing set S to become union of itself and set T. Therefore, all elements of T that are not already contained in S should be added to S. We note that this in-place operation may be implemented more efficiently than if we were to rely on the first form using the syntax of S equals to S bar T, in which identifier S is reassigned to a new set instance that represents the union. For convenience, Python's built-in set class supports named versions of these behaviors with S.union T equivalent to S.bar T and S.update T equivalent to S bar equals T. Yet those named versions are not formally provided by the mutable set abstract base class. So in this one, right, for the or, where we support the bar, we have the result is equal to a type, the same type of self that is empty, right? Create a new instance of that concrete class. For every element in the self object given, we add element to the result. And for every element in the other, we also add that element to the result and return the result. So just combining union the sets together into a new return value of result. An implementation of this behavior that computes a new set as union of two others is given in the form of dunder or special method in code fragment 10.15. And an important subtlety in this implementation is the instantiation of the resulting set. Since the mutable set class is designed as an abstract base class, instances must belong to a concrete subclass. When computing the union of two such concrete instances, the result should presumably be an instance of the same class as the operands. The function of type self returns a reference to the actual class in instance identified as self, and the subsequent parentheses is the expression type self with these parentheses call the defaulter constructor of that class. In terms of efficiency, we analyze. Hey, my dog came in and say hello. Hey, Tim. Will there be a graveyard shift today, Tim? Potentially. I'm going to a concert. It's going to be a late night concert. It starts at 9. So that's why I'm streaming a little bit earlier today. So I'm going to a concert. And then, so if I get back in a reasonable amount of time, I usually stay up pretty late on the weekends anyway. So if I get back and I'm not too tired and I want to code, then yeah, I'll come on and code up with you guys. Oh, I forgot to start the Twitch. Shoot, my fault. Hello on Twitch. We are streaming live, 4th of April, 2025. We have already been streaming for 30 minutes, been reading this chapter, but my dog's being funny in the background. But yeah, appreciate you guys being here. So yeah, if I come back from the concert tonight and I have some juice in me, I'll come on for a late night and maybe we'll play some Minecraft too. But for sure this weekend we'll be playing some Minecraft. I want to play again. I want to make just a regular survival world and build it with you guys in the background and for fun. In terms of efficiency, right? So what this is saying, right, in this function is we we get the type of the object of self, and then we call its constructor and construct that type, and then save that as result. So this will make result equal to a empty set, if given as a set, right? For this mutable set. It's fairly straightforward. In terms of efficiency, we analyze such set operations while letting n denote the size of the set and m denote the size of the set T. For an operation such as set or s bar T, where we're right, which is this up here. If the concrete sets are implemented with hashing, the expected running time of the implementation of code fragment 10.15 is O of m plus n, because it loops over both sets, performing constant time operations in the form of a containment check and a possible insertion into the result. Our implementation of the in-place version of a union is given in code fragment 10.16 in the form of the IOR, right? The in-place OR special method that supports the syntax of bar equals of this T, where we'll update the set of S with elements that are found in T that aren't found in S. Notice that this is the case, that in this case we do not create a new set instance. Instead, we modify the return the existing set of S or self after updating its contents to reflect a union operation. The in-place version of the union has expected running time of O of m, where m is the size of the second set, because we only have to loop through the second set. So for every element in other, right, we add the element to S here and return an element. Right, if this is a set, the add operation doesn't, it'll just pass over, right, via here. It won't actually raise any errors, so we can just add, and it'll add all the non-existing sets from other into self. All right, we are almost done with the chapter here. Implementing sets, multi-sets, and multi-maps. Sets, although sets and maps have very different public interfaces, they are really quite similar. A set is simply a map in which keys do not have associated values. Any data structure used to implement a map can be modified to implement the set ADT with similar performance guarantees. We could trivially adapt any map class by storing set elements as keys and using none as a irrelevant value, but such an implementation is unnecessarily wasteful. An efficient set implementation should abandon the item composition that we use in our map base class and instead store elements directly in a data structure. Multi-sets. The same element can occur several times in a multi-set. All of the data structures we have seen can be re-implemented to allow for duplicates to appear as separate elements. However, another way to implement a multi-set is by using a map in which the map key is a distinct element of the multi-set, and the associated value is a count of the number of occurrences that element within the multi-set. In fact, that is essentially what we did in section 10.1.2 in computing the frequency of words within a document. Python's standard collections module includes a definition for a class named counter that is in essence a multi-set. Formally, the counter class is a subclass of a dict that with the expectation that values are integers, and with additional functionality like a most common n method that returns a list of n most common elements. The standard dunder iter reports each element only once, since those are formally the keys of the dictionary. This is another method named elements that iterates through a multi-set with each element being repeated according to its count. Right, so this is kind of similar to that, like the duplicates, like is duplicate Python or Leet code problem and stuff. So multi-maps. Although there is no multi-map in Python standard libraries, or what was it? Yeah, is duplicate? No, is it Tucson? Yeah, Tucson, I mean. Multi-maps. Although there is no multi-map in Python standard libraries, a common implementation approach is to use a standard map in which the value associated with a key is itself a container class storing any number of associated values. We give an example of such a multi-map class in code fragment 10.17. Our implementation uses the standard dict class as the map and the list of values as the composite value in the dictionary. We have designed the class so that the different map implementation can easily be substituted by overriding the class level _ map type attribute on line 3. So in the multi-map class, we have a dictionary, which is this map type. On the initialization, we save map as map type instance. And the number of elements is 0. We save iter as for k secondary in self.map items. For v in secondary, yield the key element. For value in secondary, yield key and value. So this will just yield the key with all the associated values, which are housed in a list under that key. Okay, so this is similar. We were using a multi-map in our first iteration of the small business manager when we were housing, stuff in JSON. We are currently so JSON does a lot of this. All right, you guys, give a thumbs up for that. We have completed finally. Oh my gosh. We are finally done with chapter 10 of this book. This is by far the most dense chapter so far. It goes this, then trees, then recursion, then probably like linked lists. But I didn't find linked lists that hard, to be honest. But this one was rough. This one was by far the hardest chapter so far. And it was one of the longest ones too. Woo! We finished chapter 6, or chapter 10. Leave a thumbs up on the stream. Let's get some hearts in chat here. I'll spam a few. Spam. We finished chapter 10 here. All right, we'll work on some exercises here on and off and try to get some exercises done in this chapter. We'll definitely need some practice here. But let's go ahead and move on to the Leet code. Not here. Hey, Roeth. How's it going, dude? Welcome back in, man. Awesome to hear from you. Okay. So I did some studying on 111, and I think I can solve it. Okay, so I did some studying on this one. Off stream here. So this is my thinking. So let's first establish what we know about a node. Like, we need to understand what, if we're iterating, obviously, in some sort of fashion through this tree, we're going to land on nodes. So what kind of conditional checks do we need to take place on each node, right? Well, we're not associating anything to do with the node's values here, so we don't need to worry about that. We're not associating, so we don't even need to worry about that variable of value for the node. We're just worrying about left and right because we're counting heights. So what is the height, right? What is the height of a null node? So this is our first condition. What is the height of a null node, right? Well, the height of a null node is 0, okay? That has no height, okay? Well, what's our next condition? What's our next, this is our base case, but what's our next, another base case, right, of our check? Well, what's the next step up from a null node? Well, just a singular node with no children, right? So a leaf node is equal to a height of 1. A single leaf node has a height of just itself 1, right? Now, let's go one step further. Okay, we have a node with 1 child, right? well, what does this node have in height, right? Well, we know that a node itself has a height of 1. So, but it has a child attached to it, which also has a height of 1. And that could have a child attached to it, or multiple children attached to it. So we'd have to say 1 plus the height of the child, right? It's the 1 itself for the actual parent plus the height of its child, okay? Which in this case, if it has a child, it'll be its left child because, well, in this case, actually, it looks like it's kind of random. It's 9's over here, 15's over here, 7's over here. So if it was, okay. So then our fourth condition, our last condition for a node, is if a node with 2 children, okay? Well, this one's a little bit more complicated, but it's not that complicated if you really think about it, right? It's still similar to the one before where we have 1 plus, right, for this current node here. Now we have 2 children, but for computing the min height, right, for the min height, it's going to be the min of child 1 and child 2, right? If we're returning recursively height values, right? So that's the logic for a node with 2 children, where you have 1 for the node itself as its height, and then for computing the minimum height, right? If you wanted to know the maximum, you could take the maximum, right, or whatever. But we want to know the shortest path from its child that was to a null node position. So we'd have to take the min of either of these positions. So I think that is all the logic that we need in order to actually solve this problem, right? So let me bring this over here. And let's do this. Well, Mike, I was thinking of randomizing a number between 0 and 5 and hoping for the best. That's funny. Okay. So let me bring these conditions over here. So we're going to need... So I learned also that you don't have to create a class function here. You can, and then reference via self every single time. Like, you don't have to do this, right? I can just create a function within this actual min depth that can just be called within itself. So what we can do is call a function within min depth and not even reference self of this class, and then everything is local here in min depth, not within the class level. So I didn't know that at first. Okay, so what we can do here is we can evaluate our, we need a helper function, right? So this will be our helper. And it's going to take in some root. What is the helper going to take in? Not root, but we'll just say node, I guess. Okay, so our helper function takes in some node. We have then we evaluate our base case. So if node is none, right, we're going to return 0, right? A null node returns 0, right? That's our base case, our smallest case. We then have, so now we need to have our leaf, do our leaf nodes. So if, no, we're going to do our recursive call, right? So we need to, if node is none, we return 0. So we have a node. So let's go ahead and get a left is equal to helper node dot left plus and a right equals to 1 plus helper node dot right. Okay. So we recursively call helper, add the 1 onto for the node itself that we're currently on, and then we can evaluate these conditions. So, right, because if any of these come up to be so this returns 0. So if this comes up as none for node.left, this returns 0, gives left equal to 1. So let's just call helper.left, helper.right first. Then say if not left and right, so if we don't have both, meaning we're a leaf, so this is a leaf node. If not left and right, a leaf node returns 1, right? If, hold on one second. If not left or right, in the case where you have one or the other, one child. If okay, so let's handle the other case. So if left and right, we're going to return 1. So if left and right, where you have 2 children, we're going to do this here. Return 1 plus the minimum of child 1, child 2 path. So 1 plus min left, right? Because these are going to house the heights up to that point. So it's going to say 20 is going to contain a 1 and a 1, or a 1 here. So we're going to call, and this is going to be a 1. So 15 will be 1, 7 will be 1. Those are returned back to 20. We take the minimum. Well, they're both 1, so we can just add 1 to 1, returning, this has now a height of 2. This gets passed back to here, and that gets added to 1 for a total path height of 3. Okay, now in the final case, right, where you don't have any, you have both of them, or you have one or the other, right, either or. So this is the trickier part. I had to kind of think about this. We can kind of use some Roeth, I remember solving this the same way you, but now I think we can do it better using BFS and then keeping track of heights and left and right whenever we find a leaf and return the height. Yeah, interesting. Hey, Prax, dude, what's going on? I'm at work on break on work. No, no worries. Where do you work at? What kind of work do you do, Prax? So if left and right return one. If if not left and right return. If left and right return one plus min, right? Else we're going to return. So this is two children, right? Oh, I love Taco Bell. Nice. My brother used to work there. His senior year of high school. With random number generator, 7 out of 53 passed. Nice, dude. That's not that bad, actually, for random numbers. Nice, 27 out of 53 with your initial attempt. That's awesome, dude. What kind of car are you looking for? Hey, Chetty White, how's it going? Yeah, we read DSA in Python. We just actually finished chapter 10 today. We just finished up reading chapter 10. We've been on this chapter for a few weeks now. It's a long, dense chapter. And I break it up with, and I also take notes. So actually, speaking of which, let's go git add, git commit here. Finished chapter 10 reading. And then commit. So if you guys want access to these notes, they're on my, git push. If you want access to these notes, they're on my GitHub. I just pushed my latest chapter 10 finalized notes here. You can look at them in Markdown. A lot of great, this one's really dense. Chapter 10 on hash maps. Look at all these notes. A lot of notes, really good notes though. Really tried to detail it for you guys. RSX type S. I drove a 370Z my freshman year of college. My senior year of high school, that summer I bought a 370Z at a salvage yard, and it was in really good working shape. I just had to fix a couple of things, and I drove that around for a few years, and then I sold it. I also had a Toyota Corolla, just a cheap old 2006 one that I had originally, and then I sold the 370Z before I went to college, and I took the Corolla with me. And then I sold the Corolla for a Range Rover Evoque, and then which it sounds way more expensive than it was. It was only like 15K back when cars were a lot cheaper. And then I sold the Range Rover Evoque for a red 2016 WRX, and then I sold the WRX and then went carless for about a year and a half, 2 years almost, and then I bought the Prius, the 2010 Prius. Nice, Chetty White. This is a great time to jump on in here, dude. Yeah, insurance. That was the kicker for me. There was pretty high insurance too for my age back then. I had it at like 19, so it was, yeah. It was all black. It was really nice, but yeah, I missed that car though. Okay, let's go back to our Leet code problem. So if it's one child, what do we want to return here? That's the thing. So how can we say we want to return the child, the singular child? So return 1 plus left if left, else right. So if left, you return 1 plus left, else you return right plus 1. I mean, you could also say this a little bit more clean, like not cleaner, but like just more basic. You could just say if left, return, if left, return um, 1 plus left, return 1 plus right, right? That's essentially the same thing. But we could shorten this up and say return 1 plus left if left, else right. Cool. So that is the check on the leaf node. So if not left and not right on the helper recursive call for our base case of 0 on a none node, if not both of them, we return 1, we found a leaf. If as 2 children, if left and right, we return 1 plus the minimum path or height pushed back to us recursively from left or right. And then if one child, we return 1 plus left if there is the left, else we return the right, depending on which child it was. So now we need to actually call this function. So let's call helper on root. Is it self.helper? Let me just call helper. Just call helper on root. Bro is addicted to car flipping. Yeah, it was a phase I went through for a while. I broke it though. I just drive a Prius. I'm gonna drive it into the ground. Was looking at the Prius too. My sister gets like 50. Yeah, exactly. That's why I like it. I'm all about saving the money now because I like to buy stocks. So I'm addicted to buying stocks now rather than flipping cars. So anything to save money so I can buy stocks is pretty much the goal. So yeah, the Prius is great. Also, my goal, I also want to put in a converter. Is it called a converter or is it a? I can't remember what it's called, but you can tap into the 12-volt battery, and then with some sort of device, I think it's a convert. I don't know. And then what you can do is you can put the car into the hybrid mode, and then you can get access to like full-on plugs and like you can plug in device. So like you can go camping and car camp pretty easily with the Prius. As well, and then it doesn't use hardly any gas to just kind of occasionally power on every like half hour to just juice back up the battery a little bit so you can keep using it. And the battery does all the AC, all that stuff, so you can get AC and heat while you're sleeping at night in the cabin and maintain it for like I think it's only like $1.50 a night in gas. So it's really cool to like camp in. I really want to try it. Okay, so we're calling helper.root. Is that what we should do here? Chetty White, speaking of stocks, have you ever thought about building a program that could help you with stock choices? Um, it's just difficult it's honestly hard, I think, with stocks and like recommending because I think people walk the fine line of like financial advice and then like lawsuits and like liabilities on that. So if you develop a program that suggests like certain stocks, then it could potentially like backfire maybe. Obviously, you could have some disclaimers or whatever. Um, but yeah, I don't know. I've totally actually thought about that. I've wanted to think of like getting into some like trading algorithms and trying to like get into back testing. I don't do a lot of like technical analysis really. I mainly trade based off of like large scale news and like media and I think that like social media and is just as much of a factor, especially in today's modern age, into especially now that a lot more younger people, Gen Z, young millennials with a lot of social media experience and access is starting to really get interest into stocks like myself. I'm just picturing myself as kind of like sheep almost. Like if I'm doing it, then a lot of other people are going to it. If I'm a little bit earlier, then that's great. But so I think I am a little bit earlier. Like a lot of people in my generation are starting to now kind of figure out about stocks when I was kind of already getting into it back when I just turned 18. and stuff, and especially people younger now, you'll see a lot of people that are now like freshly 18 are starting to really, it's becoming a more trend where people are starting to pick up these terminologies and stock understanding way earlier in life. And so I think that, social media with the youth is going to play a present heavily into like, you know uh, momentum movements and like and things like that. So I don't do a lot of technical analysis per se on like looking at charts and stuff like that. I guess I just mainly follow the price, a lot of price action. I watch a select few stocks in my portfolio every single day, and I kind of have a mental understanding about what kind of levels they like to kind of reside at when it's kind of a more of a feeling, because I've been watching these stocks for almost like 5+ years now, just some select Mag 7 stocks and some select long-term holds like Hood or Kava and things like that, even though Kava kind of just IPO'd a few like a year ago. But I've been watching these stocks for a while, and really kind of getting an understanding about where they like to be, where they're comfortable, where it's kind of overextended or underextend or like underperforming or undervalued. And so it's more of like it's kind of stupid, but it's kind of like a feeling at this point rather than like technical analysis per se and like mathematical equations behind it. And just gauging like obviously societal fears and stuff like that. It's also a bad thing with social media that month where pump and dump were popular was terrible. So many kids lost money. Yeah, dude, that's crypto, man. That's why you got to stay away from that stuff. I personally, I don't ever give like advice about this kind of stuff because it's not my place and you can do whatever you want. But I don't play into crypto at all. I have a little bit just because I was given for free through some programs through the brokerages and stuff, but I don't play it. I don't buy it personally. I I I buy things. It doesn't have any tangible product. Yes, it could. It is like money doesn't actually have any tangible. It just has a belief system. That's really what supports money is the belief in that it has power of itself. But that's taken generations to instill in people. So Bitcoin could definitely and crypto get there. It'll just take, like I said, like generations to instill the value into people, like money is, because it is fake. It's not real. It's just pieces of paper, but it has value because people derive value in it and or from it. And um, so it's very similar. So it will take maybe some time and things like that. But I personally, I just, I like products. I like um, goods, services that people like, that help people. I also like to think about ethics too when I do stocks and stuff. So I really like to consider those factors as well, especially when determining companies and supporting certain CEOs. I really like to have support people with my money that I feel are going to make a difference in the world, whether in positive impact, hopefully, um, with their products, or whether or not their products are just good, if they're like consumption wise or not. Fasten your seatbelt for Monday. Praxa is playing the XRP game. Oh no, let me tell you about something with XRP. I've got a coworker who's got about his entire 401k into XRP. And let me tell you, when it was booming, he's been telling everybody for a while, you gotta buy, blah, 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 you gotta buy. No one's. And I knew it would probably pop up everyone at once in a while and give him some value, but he'll never sell it. I mean, he's in that loop. But he was going nuts, let me tell you, when it was starting to go crazy, and now it's really actually held up quite nicely from what I've been watching. It remained around like 220, 240, above $2, which is pretty nice. It's decent that it's having some of that support hold, especially in the climate, even though they're unrelated. But um, he's got a full entire 401k in that thing. It's crazy. If you ever decide to do that project, I'll definitely be here to see and learn, even if it's just for you to test yourself. Yeah, for sure, man. Chetty White, have you seen the current project that we're working on? This is my current project. Let me show you. So we put in a couple hours on this one yesterday. So this is my current project where you take in inventory items. They have various attributes that are associated with them. You take in expenses as well. Then you can transact those individual inventory items via their item IDs associated right here, right? And then what you can do is then it'll automatically populate income statements. So we're working on this page right now. And right now, my functions for some reason are not filtering appropriately for the year. They're just dumping every update onto the 2025. And so I need to debug a little bit and figure out why I'm not updating for the 2024 on transactions. As you can see, so it's a little bit buggy right now. I don't it's works for just 1 year, but I need to fix the filtering for just this. But we built this entirely in Python live on the channel from scratch here. So this is what we've been building here. We got to solve this problem though here. Okay, I think this is done though. No. Oh, I'm returning null no matter what. Zero, zero. Huh. Huh. What am I doing wrong here? See you, Prax. Thanks for coming in, man. I appreciate you coming in on your break and hanging out with me. You're awesome, dude. Nice. Sold bought 40, sold at 95. That's nice, dude. Awesome. Yeah, I bought Palantir also at, I think I got in at, I was pretty late to the game. I just got in for a quick scalp. I think I got 60 to 80 on options. So I didn't play big though. It was only like, $1,000 or something. But yeah, I caught a move on it a few times, a few overnight swings. But I knew it was overinflated. I just had a feeling this thing was gonna pop, and it did. Same with Robinhood. I was a real big investor in Robinhood around $18. Rode it all the way up to around 56, 60 on the max, and sold. I was selling off from 45 up, and then now I'm kind of starting to get my average again, around the $30 mark. Okay, so this is not working. We're just returning zero. Why? Anyone know why this one's getting a little funky? Why we're not getting the right values here? Turn helper. We're just getting zero back on root. Huh. Just trying to cook here. Tim, I need your help. What am I doing wrong here? What am I doing wrong here? So if the node is done, return zero. Left is equal to helper. So, oh, okay. So if node is none, return zero. Left is equal to helper left. Right is equal to helper right. If not left and not right, return one. If left and right, return one. Else, one or the other, return here. Huh. We're failing a base case here. Anyone know what we're going wrong here? Anyone got any ideas why we're failing here? Tim and Tim, I need you. I don't want to fight you. I need you, Tim. It might be right here because we're calling 1 plus left if left, else right. It might be like order of operations issue. So let's say if left, return one plus left, else return 1 plus right. Aha. Okay. So it was that. So then oh, here we go. We're a little slow. O of n compared to other people's solutions. I'll use a deck. Deck. They append the root value. They say depth. While you have values in the deck, increase depth on each loop for whatever in the range and length of the deck. We pop the left one on the node. If no.left is none and no.right is none, return depth. Oh, so on this one you're just tracking depth values and returning and looping using and doing depths and returning depth. All right. Yeah. So this one, they use a deck basically to pop left a node if one goes in. So they're not using recursion here. So pop left if node dot left is none and node dot right is none, return depth. So you go each depth, so you append the root to here, you go into it, into the while loop, you increase the depth by 1 because you have a root. For blank in the range length of, so 0 to 1 in this case, for root, you pop the root off, save it as node. Huh. Tim! My man, you did it too. Nice. Did you have a similar approach here? All right. Sweet. All right, cool. We solved that one. I did do some research on this one beforehand because we were stumped on it a few days ago. So I did do some research on this type of problem and kind of the what I on this kind of part here. I got some help on like what I got some guidance on, try to break down what are all the conditions. There's four of them. What are all the conditions of a node you'll pass on, and then try to determine the return values of when you land on one of those nodes. So that's what I did here, and that really helped to put it into writing here. In 10 less lines, I used max. Okay. Interesting. Well, yeah, post yours in the Discord. I'll take a peek at it. Cool, that one's cool. Interesting. Let me go back to here. Problems. Easy. Path sum. More trees. Come on. How many tree problems? Good Lord. Given the root of a binary tree and integer target sum, return the true if the tree has a root to leaf path, such as adding all the values equals the target sum. Ooh. Ooh. That's interesting. We'll take a stab at that one tomorrow. All right, you guys, this one was a little bit shorter than normal. I just do have a concert I got to go to. Me and my girl, she got me some tickets to a concert for an artist that we like. We're going to go ahead and enjoy that night tonight. I want to just at least hop on for an hour or so, a little over an hour, and do some reading into DSA and Python. I wanted to finish chapter 10, which we did, so leave some thumbs up on that. Really appreciate you guys, hanging out with me and reading the book over and over again. The book stuff, it's not that entertaining, I know, guys, but this is where the meat and potatoes of all of our learning is coming from, is these books. So if you really want to, I'm not going to Post Malone. No, is he here tonight? Oh no, is he here in the Bay? I'm screwed if he is. The traffic's gonna be bad. Is he in here? I don't think I would go to a Post Malone concert. What day is this? July 1st. Okay, no. Not today. Hey, Chetty White, thanks so much for coming in, dude. I appreciate you joining me here. Yeah, so tonight, if I come back, we'll do some coding, live coding on our small business manager. And we'll do a late night after hour session, and we'll fix that bug on our actual or income statement where the other years than 2025 aren't being populated correctly. So as you can see, we're loading transactions here, $100 worth, all into 2025, even though these are all 20, even though some of these transactions are for items that took place in 2024. So we need to fix that bug that we got going on. This item here should be populated as $10 on the 2024 income statement for gross sales because we sold it. But that's not working appropriately. But yeah, we've been writing this program live on the channel in Python, and this is our CS50X final project. Just check if there's a Warriors game. Yeah, it's hopefully not tonight. All right, thank you guys so much for joining me tonight. I'll potentially post in the Discord if I come in for an after-hour session later tonight, probably around, honestly, like 11:30 p.m. It's going to be pretty late if I do. So, but I will hop in tomorrow. Yeah, this is a GUI, graphic user interface. This is where users can interact and see data and, upload item information and add them and whatnot and refresh and stuff. So it's really, really cool, Chetty White. All right, you guys, thanks so much for joining me here. I'll see you guys later tonight, potentially. Let me know what you're working on. I stream every single day around 7 p.m., so please follow along if you're here and new. The concert's not till, I think doors open at 8:30, so we're going to leave here at like 7:45, so I got about 30 minutes here. Nice. Yeah, we took about 2 days live on the channel here, Chetty White, to really give a deep dive into Tkinter. I watched a ton of videos. I read a ton of stuff on the Tkinter forums, And so we were able to learn about Tkinter. The hardest part about Tkinter, honestly, is very similar to like other frameworks. It's not a framework, it's a library package, but it's very similar to like Flask and stuff in terms of like the get and things like that. It's a lot more simple in terms of just a method. There's no like post or what methods in terms of get or post. It's just gets and stuff. But using the get method for certain widgets. But the hardest part about it was learning how to position things in the windows using the place, the pack, and the grid. That I took a couple of days to kind of wrap my head around that. And once I realized, oh, I can manipulate grid weight and column weights to determine, kind of like in Excel, how you can merge and center items into more than one cell. So once I wrapped my head around that, it became really easy to build this out. And we've got it really working here, and it's a cool project so far. But anyways, that's enough of my yap. And thanks so much for coming in, Mahan. Thank you so much for being here. Chetty White, Tim, Coach Mo, Prax, you're awesome. AJ, thanks for coming in, dude. I think AJ said something earlier. I forgot to see. AJ said, I've seen zero use for crypto other than enabling crime. Yeah, that's why I don't invest in it, for real. It's too much fraud going on around that sphere. I don't really want to support that. Rohit, thanks so much for coming in. Glime, Winghong, Rohit, you guys are awesome. All right, guys, I'll see you later tonight for potentially some late night coding and some Minecraft. Thank you so much for being here on the early stream. See you guys.